Velo? Hello?
Hello, good evening. All are requested to come in front. We are going to resume in couple of minutes. I request Dr. Akhilesh Jain to take over here for the lecture.
इसको हटा देता हूँ सर। आपका पीपीटी तो नहीं है? मेरा पीपीटी नहीं है। अच्छा वो तो ऑनलाइन ही जोड़ेंगे उनका। अच्छा ठीक है सर,
उनको जोड़ दीजिए ना।
नहीं पहले आप बोलेंगे ना, उसके बाद हम उनको दोस्त। हेलो,
बिगड़ा तो नहीं है, एक बच्चा खाना है क्या?
Yeah, welcome, Mr. Pantaleo. On behalf of INPAC 2025 India, I welcome and I thank for giving time for your lecture. So today we are going to hear one good lecture from Mr. Pantaleo Raimondi. He has been a renowned name and he has worked in many fields of this particle accelerator, including RF system, electron accelerator, microtron, and he has vast experience in the field of all core fields of the particle accelerator. And during his journey of this career, he served very famous laboratories in the field of these accelerators like ESRF, Grenoble. In fact, he did his graduate as a part of Sun project. And he also served in Italy in this Italian National Agency. And recently, he served also as the PIP2 project director in Fermilab. So without taking much time, I immediately invite Mr. Pantaleo to deliver his talk. Next, I give mic to Mr. Pantaleo, please.
Okay, many thanks for the nice introduction. First of all, can you hear me? So can you hear?
Pantaleo, can you please speak little bit?
Can you hear me? It doesn't look like. Hello? Hello? Can you hear me? Hello? Hello?
Yeah, we can hear you.
Okay, very good. So is okay the audio? Can I share my presentation?
Yeah, please proceed. You may share your presentation now.
Okay, do you see it? See it? Hello? 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 Something.
नहीं.
Hello, can you hear me?
Yeah, we can hear you.
Can you see the presentation?
Not now. Yeah, just wait. Yeah.
Something is. Do you see it now?
No, still we are not able to see it. Have you shared it?
Okay, I'll try again. Share.
We are observing only blank screen.
Sorry. Sorry for that. Yeah.
Should we open your presentation from this side?
No, I think I can. I think let's try one more time. Now. Do you see it now?
Not yet.
No, not yet.
Strange because I'm in share mode. You see nothing? I'll try another thing. Share. Stop sharing. Let's try like this. Share. I'll
just wait for 15 seconds. Your presentation is going to come. Just share it and wait for 15 seconds.
I'm sharing the whole screen. Do you see it?
Yes, we are getting it. Yes, we are getting it.
Okay, then
Please go ahead.
let's do it like this. Do you see it now?
Yeah.
Yeah, now we are able to see you. Yeah, you can please proceed now.
Okay,
We are
okay,
able to
thanks a
hear
lot.
you.
Yes, somehow sharing the presentation did not work. So, but sharing the screen it does. So, okay, so I'll try to catch up for the time loss. I apologize. So, in this presentation is let's say is a lecture, and I will just describe how to possibility to design and eventually build light sources that are even that produce brightnesses around 3 orders of magnitudes higher than what has been achieved so far with DBS, APS-U, this say the 4th generation upgrade. So, and during this presentation, I will highlight many interesting topics, bottom beam dynamics, and on insertion devices. Insertion devices is going to be extremely interesting because the all what I'm going to describe about insertion devices is really applies to the present machines, to the present upgraded machines. So again, as I mentioned, the goal of this study is to see if it's conceivable to further improve the brightness and the flux by many order of magnitudes with respect to the present state of art. And also it comes together the improvement of the coherence fraction, so reach levels of around 90%, and also improve the longitudinal coherence. So this is going to be very important, and possibly extend the beam mode portfolio. So in particular, capability of delivering picosecond bunches. And myself, I'm very keen to design machines that have very large dynamic aperture and lifetime, really to minimize basically the request from the injection complex, and have more stable beam and minimize also the overall radiation footprint of the machine. So how a machine like this could be conceived? So the machine, the lattice could be actually split in different pieces. So you can conceive a machine where you have arcs that are designed just to deliver the minimum emittance and energy spread. And the arcs also, they will provide the chromatic correction section for the arcs and the straight section. And the straight sections actually are optimized for inserting insertion device, short straight sections where you put IDs in the straight sections. And so I will show you momentarily what does it mean. So let's start from a arc, a low emittance arc. So as everybody is familiar, a lattice that provides the best emittance with the minimum energy spread is a photolattice. And as you see here, a photolattice has been optimized in order to have very large dynamic aperture. The optimization is done like this. You take a photolattice, but you don't have sextuples at each location, at each quadrupole. So in this lattice, you have 10, the periodicity is periodic over 10 dipoles. Then the cell basically reproduce itself thereafter. And on these 10 quadruples and dipoles, you have only 6 sextuples, actually 8, because the SF are split around the QF. So those are all what you need in order to cure all the detuning induced by the sextuples, by the nonlinear element. So, and there are enough degrees of freedom in order to cancel all the first order detuning in the horizontal, in the vertical plane, and in the XY plane. And obviously you also optimize the emittance, and the emittance is optimized by choosing the best horizontal phase advance, and as you see, the vertical phase advance zeros the vertical detuning. So once you do this and you choose the proper values for these lattices, you ended up with a machine that with a lattice that is extremely anharmonic and achromatic. So you see here the bandwidth for this lattice and exceeds by far extend 3-4%. Actually, these lattices goes up to ±6%. And if you simply do, I do this kind of starfish plots where I really track here the tune, horizontal tune is chosen like 0.2, for example, and then you really track a particle for 5 turns. So this is the original coordinate, 1, 2, 3, 4, 5 turns. And you see for different amplitudes. If after 5 turns the dot comes back to where it was, this means that the particle by definition is stable. So this is a very quick way to understand first of all what are all say the detuning and higher order nonlinearities or in the lattice, or you can say resonance driving terms is equivalent, but here everything is in this function, everything is there, and also to really optimize the dynamic aperture right away. So I need only 5/3 basically when I do this. And you see actually that the machine is completely linear in all planes, horizontal, vertical, and in the XY plane. So I want just to stress that this is equivalent to search for a time-independent solution. So if you find a solution for a particle, for an electron that is time-independent, by definition, the particle is stable. So this I've been using this kind of trick for all the optimizations from here on, and also obviously for past machine. Actually, I want to show here something. Again, you see here, this is tracking done in the XY plane. You see that it's roughly linear, the machine, but in principle, you can even infer all the high order resonance driving terms from these simple functions. So this kind of lattice has been targeted to deliver an emittance of the order of around 34 picometers, and with partition number equal 1. So this machine, actually, this is a study that I did for SLAC, where the ring is 2.2 kilometer long, and the arcs are about 1.5 kilometer long. So you take this kind of cell for it's 14 meter long, and you put it in 100 of these cells to get 1.5 kilometer. You ended up with a very small horizontal emittance and very important, very small energy spread. So this is just how to compare this with a lattice. For instance, this is the 6-band achromat that has been implemented for Petra 4, and actually this lattice is very similar to this lattice in terms of the chromatic correction. You see here the sextuples are here, these 6 sextuples, and you have the same thing here and very much similar phase advances. So, but this cell, once you, on this cell, you also impose that you want to have, at the end of the cell, a straight section and dispersion free where you put insertion device, this lattice basically gets heavily distorted and becomes something like this. But the kind of optimization is exactly the same. So you have, again, all these degrees of freedom and that I described before, and the proper knobs to cancel all the high order, all the lower order detuning with amplitudes. So this is again what I said, this kind of lattice. Basically you need around 100 of these cells, and all gradients and for sextuples and quadruples are identical basically to the one that have been used to build EBS, that are very much say state of the art. Although nowadays these numbers can be like 20% higher. So many machines that have been built have these numbers around 20% higher than this. And for this kind of machine, you don't need any octupole, you don't need any special dipole with either longitudinal or transverse gradient. So this I'm not going to discuss about the transparency condition, but for what concern the PEP tunnel, as I mentioned, you have 6 straight sections, are this one, and in this 6 straight section, for instance, you can put just a standard photolattice. For all what is going to be presented onward, so the straight sections, any sections that is inserted in the arc is inserted with the transparency condition. So this I'm not going to describe here because I described many times, but basically the transparency condition is very simple. When you insert something in the arc, you impose that whatever you insert is an identity transformation. So you insert something that is at the end n pi, n2 pi and m2 pi in both planes, and also you in the middle of the cell you also zero the derivative of the W functions of the chromatic functions. In this way, when you do this, also you preserve the periodicity of the beta function in the lattice, but you preserve also the periodicity of the chromatic function, the Montague functions, in the arc as well. So when you insert this in this way, you not just match the beta functions, but you also match the Montague function, the chromatic functions in the arcs. This is really helpful in order to preserve the dynamic aperture. So you can also insert instead of just a photolattice, you can insert in this particular case the straight sections for this example are around 120 meters long. You can insert, instead of a straight section, you can, or a photolattice, you can insert a lattice that has four straight sections optimized for IDs. And you have some dipoles in between in order to provide, say, the canting between the straight sections. You can do this also has been inserted with transparency conditions and golden phases. I will show you after what the golden phases are. The canting angle between the straight sections in this case is about 41 milliradians. I will show you that is how this is translated in the beamline layout. You can insert instead of few straight sections very long, in this case are 20 meters long, you can insert straight sections that are 7 meters long. I will show you thereafter what is the difference in performance. In this case, the canting between the straight sections is 20 milliradians. So 20 milliradians means that the beam lines have to be at least 100 meters long in order to have enough separations for the arches. So, and as you see, when you do this exercise with the transparency conditions, you still, despite inserting all these chromatic sections, you still have very good dynamic aperture, so very linear machine, and also very large energy acceptance, and very flat. So this is just a possible ring with 6 straight sections with 6 IDs each, 7 meters long each. So those are 42 IDs, and you ended up with again with a machine that has excellent performances. So this is really probably at the moment the optimum. The best design that I've seen in terms of total number of beam lines and dynamic aperture and overall emittance and energy spread of the machine. So you can also use one straight section for injection and RF, and in these straight sections what you do, you build an optic such as you have a very large beta functions at the injection. So in this particular case, you have the lattice has been optimized to have 120 meter beta functions at injection. This makes a dynamic aperture way in excess of 10 millimeters. So This means that you can inject with the standard accumulation scheme. You can also, thanks to the transparency condition, this lattice is fully modular. So at any given time, you can replace one of the straight sections with any of all the different solutions that I just shown. In this particular case, again, you have this ring made by 6 arcs and 6 straight sections. One straight section is dedicated for injection and RF, you see here with the large beta function. Then one straight section is hosts 4 long IDs, and 2 straight section host 6, actually 7 short IDs. 2 straight sections are just a photolattice. And just to say that you can have any of these combinations as you want. So I want to just mention about the transparency condition. So this is, as I've shown, say the canting dipoles that are needed between straight sections. This is very much a double band achromat, basically. In fact, a little bit optimized. Since you have dispersion here, you can add sextuplets, and this helps in order to decrease the overall chromaticity of the system, and you have to rely less on the arc sextuplets in order to correct the overall chromaticity. Obviously, this kind of sextuplets, they will somehow affect the overall Montague functions, the chromatic functions, in the rest of the machine, in the arcs. Still, there is a trick that if you have a particular phase advance between the of this section, this sextuple will not alter the chromatic functions in the arcs. So there is a golden phase. So basically you see here that if you choose a proper phase advance for this say double band achromat, what you have is again say additional transparency that makes so that if you see these are the Montague functions when you use only the arc sextuples to correct the chromaticity. Now, if I turn on the sextuples in these sections, the one that I just shown you before, you will not change any periodicity. You will not break the periodicity of the Montague functions in the arc. So this is going to be a self-consistent. And you see that what happens actually, that the Montague functions in the arcs, they get lower. Say here they were 12, here they get 10, because the chromaticity of this section is corrected by its own. So, but you have to have these golden phases. So this indeed is extremely powerful, extremely elegant. You can have 2 different periodic structures nested, each one with its own sextuples that are mutually transparent. So this is very, very, very important. So, and just to show what happens if you don't put you don't turn on the sextuples in the straight sections, this is in the double band achromat insertions, since the chromaticity that you are generating this section is very hard, it's very big, you start to see some detuning in horizontal, vertical, and XY. And when you turn these sextuples, now the arc sextuples, they are not touched. and you ended up with a much more linear machines. So you you will not add this additional detuning. So this is actually the trick to get this very large dynamic aperture. I want also to stress that for this kind of machines, they are very large and the bunch length is naturally very short. You need to really increase this, obviously, to reduce ABS and in general improve tool check lifetime. But on the other hand, when you have higher harmonic cavities, you can also use them for dedicated runs in shortening mode. So, and then you can easily have bunches that are of the order of 1 picosecond long, see. So I want also to stress this is a problem that very much all the machines have, and EBS actually has a limitation due to this, that for all the fourth generations machines, the dipoles, they move closer and closer, the last dipole move closer and closer to the straight sections. So for EBS, actually, this last dipole is right here. So this basically means that the synchrotron radiation from the dipole, no matter what, will hit the chamber in the straight sections in the insertion device, and then obviously you have to dissipate this power, and this also limits seriously what kind of insertion devices you can conceive, because basically in the horizontal plane you have this large power that is going to deposit on the chamber and has to be dealt with. In addition to this, obviously, you have degassing due to the synchrotron radiation. Again, this makes the vacuum in the insertion device section critical, and with all the consequences that we do. So this is really a problem. For this kind of solution, actually, you have a lot of space in these long straight sections, and you can really accommodate comfortably. You can have a very long distance between the last dipole and the insertion device. This means that if you put an absorber at this location, where actually the beta function is very small, you can have an absorber that is as a aperture smaller, say with the square root of the betas ratio with respect to the vacuum chamber size in the insertion devices. And in addition to this, you can also tailor the dipoles in this section in order to have, say, this one a soft band that further decrease the amount of power deposited in the chamber. With this scheme, you have, with this simple scheme, the dipoles have been dimensioned accordingly, and you can have way less than 10 watts in intercepting the chamber in the total at 10 watts in the straight sections. So this is very important, because at this point you can have really the straight section is going to be round, in the sense that you will have no difference whatsoever in behavior in the horizontal and vertical plane. Actually, you see that you have the beta functions are both matched, and the gaps for the insertion device can be the same size in the horizontal and in the vertical plane. So this, for instance, means that you can put, for instance, helical ondulators superconducting. There are many of these devices that have been are under, say, R&D around the world. So this could be really, and they are, as you see, they're extremely simple, extremely compact, and probably extremely much cheaper than the insertion devices that we all know about. So this really could be, obviously you can make them very, very long without any additional complication. So now I want to spend a few words on how the insertion devices do match with the with the beam. So as you know, this is what is the typical spectrum for third generation light sources, and the spectrum actually is very large because there are many contributions to this. One is the number of period in the undulator that is relatively small for third generation compared with this spectrum. But again, just looking to the formula, what really increases just to the derivative of this with respect to the energy and the angular spread of the beam, you ended up that the beam really makes the largest contribution to this spectrum. This is simply due from the derivative of this. So if we define the bandwidth like full width half maximum, 1/n is the bandwidth determined by the number of period of undulator. The bandwidth determined, again, bandwidth defined in this way, determined by the energy spread is 2 times 2 is 4 times the energy spread. The bandwidth from the emittance actually again is this number here is this, and actually very simply is the energy squared times the sum of the emittance. This is the angular divergence squared, is the emittance over the beta functions, horizontal and vertical. So how these numbers are for the present machines. So for what concern the former machine, the third generation machine, this emittance divided beta is among us. In particular, we had for ESRF, the double band achromat, we had two kind of insertion devices. One with high beta was about 40 meter, one with low beta was about 0.4 meter. So, and as you can see, this number is more than 1. So this means really that hardly you see any spectral line for the low beta insertion, but even for the high beta insertion, this number is very large. So now this is very interesting. For the fourth generation, by chance, I would say, these three contributions are really equilibrated. So if we suppose an undulator with about a couple of hundred periods, roughly what we have now for, say, 2-3 meter undulator, the bandwidth from the number of period is 5 in 10 to the minus 3. The bandwidth determined by the energy spread is 4 in 10 to the minus 3, and the bandwidth determined by the emittance is about 3 10 to the minus 3. And actually, when you had these two things in quadrature, they very much match what you get from the undulator. So this already tells you that if you want to have really gain here in bandwidth, this now is very much matched for a fourth generation light source, whereas it was heavily mismatched for a third generation. So the undulator was way better than the beam. So here they have the same order of magnitude. For a new machine, if you want really to improve, to decrease this bandwidth, you have to work on the two things at the same time. So decrease emittance, decrease three things at the same time: emittance, energy spread, and increase the number of periods. So that's the only way. So for these parameters, for the ring that I just described, these numbers are of the order of 10 to the minus 3, means that you need, in order really to exploit this kind of parameters of the better beam, you need to further increase the length and or the number of periods of undulators close to, say, 1000. So this means that undulators have to be of the order of 10 meters long. So, and definitely this is what I said, the best performance ever achieved when everything is matched. So you have to upgrade the beam, but also insertion devices and for sure the beam lines as well. So this is just to show the layout of this kind of machine. How does it look? At the end, it's very similar to any machine, but the difference is that if you have only 20 milliradians between beam lines, you need beam lines that have to be at least 100 meters long in order then to be able to build separate hatches. But this is nevertheless the trend that is happening anyway now. So all the beam lines really, they fully exploit the characteristic of the beam when they are longer and longer. So on the other hand, this length does not really add cost, because if you see this kind of building is very similar to the standard ones. It's only that you have these tubes 100 meters long before in between the ring and the experimental buildings. So for what concern, if you have 40 milliradians angles, obviously things are very similar, but you have a larger separation between the hatches, so it's definitely something feasible. So I spend a lot of time showing that we can have a machine that has a much better longitudinal coherence. So in principle, this means that you might gain about a factor 1000 in brightness if you don't use monochromators. So just to stress, the monochromators, they limit, they only take 10 to the minus 4 in terms of the bandwidth after the monochromator is 10 to the minus 4. So you really cut, say, more than 90% of the light. If you can remove this, automatically you get 1000 times more brightness. But we have to see if there are beam lines that can, there is a case for beam lines that can operate monochromatorless, but they will have an energy spread, say a bandwidth of the order of 10 to the minus 3. If there is a scientific case for this, you can get up to a factor 1000, otherwise you get only factor 100. So I'm just jumping to the conclusion that this kind of machine with large longitudinal, with a very big longitudinal coherence could really represent a new quantum leap for X-ray science based on synchronized sources. So thank you. You have questions? Can stop sharing.
Yeah, Pantaleo, we have one question from one audience. नहीं यही से मैं बुला लिया यहाँ पे. हाँ ये.
Hello.
Sir, question is for Pantaleo now.
Hello, sir. Dr. Pantaleo, are you going to operate the machine in sub-picosecond?
यही आ जा, आवाज नहीं आ रही है.
तो बंद कर दीजिए.
आप तो यही खड़े होते.
Are you going to operate the machine in routine operation in sub-picosecond bunches?
As I've shown you before, since the natural natural bunch length is of the order of 1 millimeter, so say 3 picosecond. And normally what you do is
Pardon,
you
sir, voice is
the
not
high.
clear.
Sorry.
Can you please repeat? We lost the voice.
Yes, so this kind of machine with this very small emittance produce a natural bunch length of the order of 3 picoseconds. So, but this is already very short for standard operation. So normally you add a third harmonic, a fourth harmonic cavity to go up to say 10 picosecond. So then you can imagine that you can have some mode of operation where the cavity is used to lengthen the bunch. So it's a standard multi-bunch case where the bunch is 10 picosecond. Then you can use the high harmonic cavity in shortening mode, and then you go down to say 1 picosecond just using the high harmonic cavity. But for this case, you have to also decrease the bunch current for sure, because otherwise the IBS is going to kill you. So this means, say, you can operate the machine with standard, say, 300 milliamps in multi-bunch with a bunch of 10 picosecond. Then you can operate with, say, 30 milliamps, 10 times lower current, but only 1 picosecond bunch length. So, and then you can have dedicated runs for people, for experiments that really work for timing mode experiments. It's very similar to what we do even at the SRF. We have the timing mode dedicated experiments, but the only thing that we change is actually the distance between the bunches. We cannot do this. And but there are experiments that they can work in timing mode only if you have, say, different bunch pattern. In this particular case, we change maybe the bunch pattern and the bunch length as the users want. So,
Okay, that means you are not going to play with the momentum compaction factor for getting the sub-picosecond bunches.
this is a very good point, very nice question. For this particular lattice, since it's a photo lattice, you can also decrease the momentum combustion by changing the phase advance for the photo lattice. So this means that you might even do it without the aim of the high harmonic cavity, or maybe you can even get even shorter bunches. But again, shorter bunches, you very much you go down linearly with the charge, actually with 1 over the bunch length. So no matter what, the shorter is the bunch, the less current you have. So, but again, there is gonna be obviously an optimum that has to be figured with the beam lines. So keep in mind that this kind of machine has way larger flux of standard machine, so probably doesn't need so much current and so much so to get the same number of photons. So,
Okay, sir. One more question. As you mentioned in one of your slide, what is the benefit for matching the second order dispersion function?
Again, if you match the chromatic functions, actually they are both Wx, Wy, and the second order dispersion. This results in the larger momentum acceptance and Tuschek lifetime. Actually, not even say there is the momentum acceptance, but also the local momentum acceptance. That is the momentum acceptance through the ring. That is actually varies. And if you have a completely periodic, if the Montague functions, the chromatic function, are completely periodic, this corresponds to the largest local momentum acceptance in the ring as well. So.
Okay, sir. Thank you.
So, I think Pantaleo, there is no more question. We cannot physically give thank to you, but virtually we thank for your useful information, which will be definitely useful for our future machine design and beamline design. And on behalf of our, once again, I thank to you on behalf of our conference organizing team and all the audience. Thank you very much once again.
Thanks a lot to you to give me the occasion for the opportunity to give this presentation, and best wishes.
Thank you.
Thank you.
I now, I now request